Hey everybody, and welcome to our video on slope fields. It's a very interesting topic. I think slope fields, they're tedious. I'm not going to lie. They're a tad tedious, but they're interesting. So that's the title of our lesson today. And we've been working with differential equations, so that is how we start this lesson. It tells us to consider the differential equation dy dx equals y. Okay? Now, we're going to fill in some blanks here. Y, this guy right here, so let me actually highlight over that Y. This is the Y I'm talking about. This Y represents the blank, 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 blank. So we have to think back to our previous studies, and I am hoping that you're thinking that since Y is equal to the derivative dy dx, that Y represents the slope of the tangent line at any value of y, because that's all we've got there on the right side of the equation, at any value of y on the graph of the original equation, y equals f of x. That's what we learned derivatives to be. They're slopes of tangent lines at a particular point. This would have to be the point right here on the graph of the original y equals f of x. Okay, let's go on to read this next paragraph. Because tangent lines approximate curves locally, we can plot short tangent line segments at various values of y. These segments will show the direction the graph of y takes. By doing this, you can draw the graph just by knowing one point x, y. So the whole idea, if I had to summarize the purpose of slope fields, if you have a differential equation that's difficult to solve by hand, you can make a slope field and get information about the original function without ever having to solve a differential equation. Okay, one more blank to fill in here. The resulting array of short tangent line segments is called a slope field, and that's what we're studying today. It's a field of slopes, a slope field or a direction field. Okay, so we're going to get right into our first example. So example 1 says, we're going to use that same equation from up above, construct a slope field given the differential equation and point below. So this is what we've been studying. We've been solving differential equations and then using the point given to find C. Well, instead of doing that, we're going to take the differential equation and construct a slope field. So check out how easy this is. So notice here I have values of y. I pick some negatives, some positives, and 0, and then I have the resulting slope, or dy dx. So we're going to filter these into the equation. So when y is -3, you just plug it there, dy dx is -3. Now let's show how that plays out below on the slope field. So what you're going to do is on this little array of dots, this is like slope field graph paper here, you're going to go to y equals -3. Now, y equals -3 is this whole line right here coming across. You're going to plot short little tangent line segments, each with a slope of -3. So it's going to be like this. Like say I was at this right lower point, and I know the slope there on my graph is -3. Well, from this point, if I go up 3 and left 1, I would be connecting this dot with this dot. And so right here at that lower right corner, I'm just going to draw a segment whose slope is -3. Again, if I were extending that line, it would come up and cross right here, and then this line would have a slope of -3. But I just want to do a little blip there. Okay, moving to the next one. Right here, if I were to go up 3 and left 1 and connect those two dots, right there is a slope of -3. And I'm going to do this all the way across. So all of these are going to be the same steepness. And listen, you don't have to be perfect here. I do try to be pretty accurate, but it doesn't have to be perfect. So do you see how when y is -3, all of the slopes of the tangent lines are -3? And now that just keeps going. So when y is -2, the slope is equal to y, so it's also -2. So when I go to draw across here, when y is -2, all the slopes are -2. So now I'm kind of connecting this dot right here if I would go up 2 and left 1, so about right like that. See how it's just a little less steep than this guy? And I'm going to do that all the way across. I'm trying to make a -2 slope. Again, doesn't have to be perfect. Okay, and now -1. Well, when y is -1, dy dx is -1. So now I need, across this horizontal, y equals -1, I need slopes of -1. So let's see here. Be like about there, there, there. Okay, see how they're getting less steep on the way up? 0 would be 0, and we know how to represent slopes of 0. We just go horizontal. Okay, and then we do the likewise here. When y is 1, dy dx is 1. So across y equals 1, I'm going to do slopes of 1. Again, I'm just thinking in my head, like when I'm like up 1 over 1. Okay, connect, just a little guy. That's how I do it in my head, just connecting dots. Oops, there we go. And when y is 2, dy dx is 2. So now I need slopes of 2. It's going to be a little bit steeper, steeper. And finally, when y is 3, the slopes are 3. So, steeper yet, all the way across. I'm careful not to smudge my pen here. So you just made your first slope field based on the differential equation dy dx equals y. Okay, so what do we do with it? Well, that's what we're going to see on the next page. So let's flip this over and continue on our merry way. So the next part says, now solve the differential equation. This is what we've been working on. Solve the differential equation by hand to see if your slope field makes sense. And this is where it gets really cool. So what we're going to do is we're going to take what we've been working on. Here's the differential equation. So we have to separate the variables. So my first step will be to multiply dx to both sides, which is going to cancel those guys out and give me dy equals y times dx. Now I don't want that y there. I'm going to go ahead and divide both sides by y. This is going to give me 1 over y dy is equal to dx. Now I'm going to integrate both sides. Remember, I'm trying to solve for y here. And from our previous studies, I think we're pretty keen on the idea that the definite integral of 1 over y with respect to y is the natural log of the absolute value of y. Because the derivative of the natural log of y is 1 over y, we can see us going backwards. The absolute value bars are there because you can only take the natural log of positive numbers. On this side, we're integrating essentially the constant 1 with respect to x, so that antiderivative is just x, and then we add that arbitrary constant c to the back. Okay, let's continue on. Now, we need to solve for y. Well, ln means the same as log with the base e of the absolute value of y equals x plus c. And so to solve for the absolute value of y, we raise e to the x plus c. And at that point, we can drop the absolute value bars because e raised to any power will be positive. So y equals e to the x plus c. And then we did this once or twice before, not a lot, but when you have e to the x plus c, we can break that into e to the x times e to the c by our properties of exponents. And so finally, we kind of take this e to the c, which is nothing more than a constant, and we bring it to the front of the equation and we go like this. Y equals, we call it capital C e to the x. So this is sort of our solution to the differential equation. We haven't addressed any particular solutions. This is sort of just a general solution to the differential equation. Now let's get particular. Let's plug in 0, 1. So when x is 0, y is 1, and that's going to help us to find this c. So that'll be our last step. Let me change colors here. So y is 1 when x is 0. And since e to the 0 is 1, we have c equals 1. And so my final answer is y equals 1 e to the x, or simply y equals e to the x. Now, watch how cool this is. Could we have come up with y equals e to the x without doing all of this work? I mean, this is a lot of work. Well, check this out. If we flip back to our slope field, we're going to plot this point they gave us, 0, 1. So let's go back over here. 0, 1 sits right here. So let's kind of boldface that point. Knowing that my original graph, y equals f of x, so I'm about to graph y equals f of x here, knowing that this graph goes through this point, and knowing that this field represents the slopes of the tangent lines on this graph, I can follow these short line segments to sketch my graph. So as I leave 0, 1, check it out. So I'm coming over here. My slope is somewhat steep, steeper, steeper. So I'm kind of increasing through here. Now think about it. If I stopped right here and drew a tangent line, it would match that little green guy. If I stopped right here and drew a tangent line, it would grab that little green guy. And as I'm coming back this way, I'm approaching these horizontal 0 slopes, which is kind of indicating an asymptote here as I approach negative infinity. And so one thing I can tell right off the bat, just from having that point along with my slope field, is that this y is equal to some exponential function, because I know the family of exponential functions has this shape. Now, would I know that it was e to the x versus 2 to the x, or 3 to the x, or something like that? That's a little bit harder to tell, and that's where you can do some investigative work here to see that it truly is e to the x. But isn't that so cool? Okay, now let's look at the last part here. It says, so y equals, and I'm going to write this answer here, y equals e to the x is one particular solution of this differential equation. Now, the last part says, well, what if you had a different point? What if y of 0 was negative 1? Does the slope field account for this? Well, let's see. Let's go back to our generic solution right here. I'm going to bring this down and write it here. So y equals capital C e to the x. Now I'm going to plug this point in. So y is negative 1 when x is 0. Well, e to the 0 is still 1, so c now is negative 1. So going back here, y equals negative 1 e to the x, or simply y equals negative e to the x. So that's the particular solution when we change the point. Well, let's see if our slope field accounts for this. So what I want to do is I want to plot this point on the slope field. 0, negative 1. 0, negative 1. That's down here. Boldface. Now let's follow our slopes. Leaving this, coming down, down, down. Coming across to the zeros, kind of looking like that. You can see those tangent lines match up with the green. Now, I'm totally curious. Let's plug y equals. Let's do e to the x. So that was our first one. And let's do negative e to the x. Here we go. There's e to the x and negative e to the x. See it? So this guy right here that I'm pointing to matches this guy right here. So as long as you have 1 point on a graph, you can definitely get some good information about your function without ever having anti-differentiated. Okay, now if you missed class today, you missed one other, I wouldn't call it an example because I let everybody work on it on their own, but you would have missed this classwork today on slope fields. So it's just another example. What you could do for me is pause the video, and what I'll do is when you come back, then I'll go through it and then you can make sure your answers are correct. That'll give you an idea if you understand. So I'm gonna go a little bit faster through this one. This time, we're constructing a slope field and our differential equation is a little different. It's dy dx equals x. So now our slopes depend only on the x value. So I've written some x values down the table, and so we'll get the slope. So when x is -3, dy dx is -3, and so forth. -2, -1, 0, 1, 2, and 3. So hopefully you match me there. Now, does the slope field match? Well, when x is -3, so that's here at -3 on the x, all the slopes when x are -3 are -3. So if I think of down 3/1, pretty steep, 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 steep. And when x is -2 right here, all the slopes are -2. So they're like this. Little less steep. And then when x is -1, all the slopes are -1, so they're even less steep. And 0 is 0, so they come flat, horizontal. And 1, 1, so now we go positive. And 2 is 2, so a little bit steeper. And then 3, 3, so even steeper coming through. Okay, now they give me an initial point here, 0, 0. So let's plot 0, 0 as our boldface point. And let's draw what we think y looks like from our slope field. So I know my tangent line's horizontal here. I leave here and I kind of, this one turns me here, so I go this way and up we go. See, slope, slope. And this way, same idea. The slopes are taking me this way, increasing. So to me, boy, oh boy, it looks quadratic. So now we will see if it truly is. We're going to solve the differential equation. So solve dy dx equals x. Well, we're going to multiply both sides by dx. So dy is equal to x times dx. This is going to be an easy one. We're going to integrate. We've got y here equals 1/2 x squared plus c. To solve for c, because we do have that point that's on the graph, 0, 0, you can see that when y is 0 and when x is 0, c is most certainly 0. So my final equation will be y equals 1/2 x squared plus 0, which is just y equals 1/2 x squared. Does your answer make sense? Well, heck yes, it does. Look at that. Doesn't that look reasonable? I said it was quadratic, and lo and behold, it is. And you know y equals 1/2 x squared has a vertex at 0, 0, opens upward, So it's looking pretty good. So we're just delving into slope fields. This is our introductory lesson, so I hope it makes sense. And I'm sure I'll be doing some more videos on slope fields as we go through, just so we have some more references. Okay, thanks for watching.